Hello everybody and welcome to my video on confidence intervals for a population mean. This video will assume that you have watched the previous video. I'm not going to cover a lot of the theory as I've already covered most of the theory, if not all of it, in the previous video. So please, if you have not watched that video, just stop this one and go back and watch the other one on the proportions. And this video should not be as long as the previous video. I hope, I promise. All right, so in this video, I will make some introductory comments. We'll go into a new distribution called the T distribution, and this T distribution is going to move forward with us. We're going to use it in this chapter to compute confidence intervals. We'll go back to the Z for the sample size, and then moving forward, we will talk about and use the T distribution in the next chapter on hypothesis testing with a single population parameter, and then we will use it in the next chapter to talk about hypothesis testing with two population parameters, which is going to be pretty much your project. So by the time we finish up on two independent populations, you will have enough to complete part 3 of your project. So with that being said, I just want to go ahead and let's get started. All right, so by method of introduction, I just want to take a look at some review material. So earlier we talked about a confidence interval, and the confidence interval is normally in the form of a point estimate plus or minus some margin of error. And talking about sampling distributions, we talked about X bar is approximately normal with a mean population mean mu and sigma over root n. So that being the case, with this normality assumption, our point estimate right here is going to be X bar. And let's just recall that the margin of error, it involves something with sigma over root n. So in our case, we're going to have our point estimate right here at X bar, and then notice that we have our standard deviation of the point estimate, and then this z-score tells us the number of standard deviations, or it tells us the number of standard deviations for X bar, how far away we have to go to the left and to the right of our point estimate. So one of the interesting things to note is that this margin of error involves our population parameter sigma. But here's the problem. We don't know sigma. Since we don't know sigma, then we're going to have to do something. So what we do in practice is we toss in S. So S is the sample standard deviation, and we'll just use that as our best guesstimate for sigma. And when we throw in S, it also changes the distribution properties of X bar. So that means that X bar is no longer normally distributed. So that means we have to figure out, if it's no longer normally distributed, then what is the distribution for X bar, and what happens to that Z alpha over 2? And based on that question, I'm glad you asked. So let's move forward to the next component. In this chapter, we will introduce what is called the student's T distribution, which, based upon your philosophical belief on life, was either discovered or created by a gentleman by the name of William Gossett, who was working with some impurities in a particular drinking substance. So just to go ahead and give it away, William Gossett worked for St. James's Gate Brewery, which is the maker of Guinness beer. And he found out that his results, his empirical results, were not quite matching up with the theoretical results. So he got together with a famous statistician back in the early 1900s, and then they discovered this thing, and they posted a paper. But unfortunately, St. James's Gate Brewery wouldn't allow certain things, so he had to publish under a pseudonym of Students. So hence, this distribution is referred to as the Students T distribution. So here is a picture of the Students T distribution, and just for funsies, I went ahead, and there is a functional form to this thing, and this is one, crazy looking function here. It involves what is called a gamma function, and then you got this stuff going on. But one of the things I want to point out is this Greek letter nu. This Greek letter nu represents a parameter to the T distribution, which we will talk about, and is called the degrees of freedom. So the Students T distribution uses this parameter, or this concept called the degrees of freedom. So let's take a look at this top curve a little bit more in detail here, make it a little bit bigger. So the idea is that the T distribution is actually based on a family of curves. And this family over here in this picture, the family is chosen by having this degrees of freedom. So as the degrees of freedom changes, the T distribution also changes. So the idea is that if you look at these curves, k equal 1 is right here, and then as the k's get bigger, or the degrees of freedom become larger and technically tend to infinity, then they will actually stop at this top distribution right here. And the interesting thing is that top distribution, when the degrees of freedom get large enough, that top distribution is the standard normal distribution. So yes, the standard normal does come back to haunt us. So this degrees of freedom, as we're going to see later, is based on the sample size. And this degrees of freedom, there's a lot that can be said about the degrees of freedom and what it is and what it represents. But in our case, the degrees of freedom is just going to be the sample size minus 1. All right, so this T distribution, I'd like to take a look at some properties of this T distribution, which looks very similar to our standard normal distribution. So let's just take a look. The T distribution is technically different in that for the various degrees of freedom. It's different in that it's either going to be short and wider. Notice that these tails get thicker for a smaller degree of freedom, and then notice that as the degrees of freedom increase, those tails will tend to thin out and converge to that normal distribution. All T curves are centered about 0 and symmetric about 0. No matter the degrees of freedom, the area underneath the curve is always 1. And as we can see on both sides, no matter what happens, the T distribution is also asymptotic to the x-axis. And we can also see that, notice this top curve right here, as we come down, this top curve, our standard normal distribution, that all the T curves right here, these curves are actually thicker. They're thicker in the tail. Okay, and same over here, notice all these T curves are thicker in the tail. And the reason why that is important is in order to get that alpha area, you have to move further out into the tail area. So that means we're going to end up by default with a wider interval. Okay, going back to our standard normal. So notice that if you want a 95% confident with these T curves, you have to come out this far, whereas with the normal distribution, you only have to come out this far. So that's one of the reasons, well, it's one of the things that Gossett was having some problems with. And as the degrees of freedom or the sample size increases, again, converge. And as we said earlier, the degrees of freedom then is related to sample size minus 1 technically. All right, so let's just kind of pull everything together. So we said that x bar was normally distributed z sigma over root n. We don't know sigma, so we threw in s. When we throw in s, that changes the distribution properties of x bar. So x bar is no longer distributed normal, it is now distributed t. So rather than working with this t critical value or this t or z, sorry I said t, but rather than working with this z critical value or this z score, we now substitute and use the t critical value or the t score, all right, and we'll also use s, and then we end up using the fact that the degrees of freedom is sample size. And going back to chapter 3, as you learned, sample size is always little n. So no matter what happens when you see little n, that's always the sample size. Whereas if you see big N, it is always the population size. So let's take a peek see at an example here. So a lab tested 12 chicken eggs and found that the mean cholesterol was about 188 milligrams with a standard deviation of 12.7. So we would like to construct a 95% confidence interval for the true mean. So I have the formula and information down here below. So we've done this before, so let's take a look and see how the exact same steps for the proportion now applies to the sample mean. So alpha is going to be 1 minus the confidence level, which is 1 minus 0.95, which is 0.05. In step 2, we're going to cut alpha by 2. We want one of those tail areas. So that gives us 0.025. In step 3, we go ahead and we can compute t sub alpha over 2. Now to compute the critical value, this t critical value, or this t-score sub alpha over 2, we can use StatCrunch. And in fact, that's the preferred method to use to compute the t alpha over 2. So again, using your t calculator, and again, you can watch the video that I have posted on how to do this in its grand and glory detail, but I'll just give you an introduction. You use this t, you go to the calculator and the t distribution. So we'll just pop in the degrees of freedom. So if you'll recall, the sample size was 12. So 12 minus 1 is 11. And we're going to, as from previous video, use the left-tailed area, and that area has to be 0.025. And when we click the compute button, it gives us this t distribution right here, again centered at 0. And notice that for this 95 degrees, we have to go out 2.2009852. All right, so notice that if you'll recall, for proportions for a 95 degree confidence, we said we only had to go out 1.96. So again, to get that same score, this guy right here, we have to go further out on the tail based on this 12 degrees of freedom. Now, if the degrees of freedom gets larger, then that t-score would become slightly smaller. If our sample size is smaller, then we have to go further out into the tail to get that t-score. So that's kind of the relationships if you go back to that previous one where I said that the tails are thicker for the t distribution as compared to the standard normal distribution. All right, so now that we have our t-score, we can go ahead and plug that in. So notice we get the 188 plus or minus, and it's common to round to 2.201. It's common to round to 3 decimals, but make sure you follow your instructions in StatCrunch. 12.7 over root n, and when we do that, this then becomes a calculator question if you manually do this, which again, I don't recommend you to do, but we get the 1.79 to 1.96. So our next step is to interpret this confidence interval. So we can come back and say we are 95% confident that the true mean cholesterol is between 179.9 milligrams and 196.1. And let's just recall from our previous discussion that 95% confident means, for example, if we were able to construct 100 confidence intervals, then 95% of those confidence intervals would contain the true population mean. All right. So using StatCrunch, again, is really nice. Notice it comes out and you just do the magic little button pushing on StatCrunch, which I will show in the video. So be sure to watch the StatCrunch video on how to do all this computation. And notice it pretty much gives us the exact same thing that we computed before. Okay, so that's the confidence intervals for the population mean, and that's how we do them. The sample size computation, let's just note that the sample size, in order to do this, we are going to work with this margin of error. So let's just recall that we have to allow an acceptable and come up with some sort of acceptable margin of error here. All right, and so then the question is, what would be the sample size to allow for this margin of error that we would like to have? Okay, so remember the trade-off with confidence intervals is that the larger your confidence level that we discussed earlier, the larger your confidence, the wider the interval. And again, since we're trying to use these interval estimates to get a grasp on the population parameter, we would like to have the amount of wiggle room to be small. But unfortunately, we have that trade-off that says the larger the confidence, the more wiggle room. So how can I have that same level of confidence with a smaller amount of wiggle room? Okay, so let's take a peek, see. So we go ahead and we accept our margin of error. What is it going to be? So then it becomes taking that allowable margin of error and setting it equal to this. Now, the problem comes in with the t-distribution, and that is, how do I come up with, this t thing? It doesn't transfer quite nicely back over. Okay, so one of the things that we can do is resubstitute and not use the t, but we'll just go ahead and put in the z, because it kind of helps when we do that, and it makes things a little simpler. So you'll notice in this case we transform from the t back to the z just for this little special case here. All right, and then if I take n and move it over here and divide by e and then square, I end up with this formula right here. So for our sample size computation for sample means, this is what we do. So let's take a peek, see. A researcher wanted to determine the mean number of hours per week a typical person watches TV. Results from the 5280 statistics survey indicate that the standard deviation is about 8.1. So this comes about probably using a pilot study, if this study has never been done before, or you can go back and research literature and you can get an idea on what the previous standard deviations, if you're redoing this type of a study. So how many people are needed to estimate the number of hours people watch television per week within 2 hours? So there's our margin of error with a 95% level of confidence. So again, our step one is that we compute our alpha level of 0.05. Step two, we cut the alpha level in half. So this is all familiar. And now to compute z sub alpha over 2. In this case, I'm just going to use the fact that we discussed previously, and it's in your book, and it's well known that for a 95% confidence that this z alpha over 2 is actually equal to 1.96, because this is one of our familiar confidence levels. Now, taking that information and plugging it in, we end up with a sample size of 64. Now again, in the StatCrunch video, I will show you how to use StatCrunch to compute the confidence or the population, or how to compute the sample size in order to do this, okay? So this is if you had to do it by hand, just to let you see all the grunt work. But again, please take a few minutes and watch the other video to compute the sample size. It'll be much easier. All right, so this concludes our video regarding confidence intervals and estimation. So now you have enough resources that you should be able to complete your required assignment. So all I have to say is adios, and I'll see you in the classroom.